Hello, my name is Volkmar Frinken. I'm with Spider, one of the two Proto-OKN teams comprising the fabric of the Proto-OKN. So the vision of the fabric is to bring everything together into one big knowledge graphs. Currently, the individual knowledge graphs and databases, as beautiful and well composed as they are somehow disjoint from each other, and the data is siloed away. So there is a knowledge graph about supply chains, there is a knowledge graph about software vulnerabilities, criminal justice insights, and so on. And so these databases, they are somehow related to each other and share some topologies, but in the end, they are distinct and have different entities. And sometimes they even have different database formats. There is RDF with Sparkle queries, there is Neo4j, which needs Cypher queries, or sometimes we only have an API access point, particularly when we talk about external agencies like NOAA and NASA. And so what we want to do is provide a unified access point to make all of these different knowledge graphs and entities in general appear as one entity. So the user, and that means it in particular, should not need to worry about the topology of the individual data or even what data is stored where. We want to provide an automatic visualization when we think it's beautiful to present this data or useful as a table or a graph. And then we also want to provide some multi-step and multi-turn functionalities. So multi-turn functionalities means that the user can engage in a dialogue with the system and ask a follow-up question to build up a more complex query or ask something about something that had been answered before. Multi-step is a single query that is so complex that it needs to be fanned out across different databases, that we need to gather some data from here and some data from there and then assemble it together before it can be returned to the user. And so in this context, Spider is one of the two teams. As I mentioned before, the other team is Frink, and we are closely collaborating to provide the fabric. Frink is more associated with the entire data management side of it, hosting the data, making sure that there is an access point where everything runs smoothly, version management, unifying the databases. Our job is more on the user-facing side of it. So that means we interpret the user query, we determine what data can answer it and where to find that data. Then we create and securely route the invocations to the appropriate endpoint to get some results back. We assemble those results and present those back to the user. So let's talk a bit more what that means, what we have. So here is a subset of all the different user queries that we expect our system to be able to be answered. There are user queries about software vulnerabilities, like which version of libgd is free from vulnerabilities, about supply chain, what I had, how many manufacturers in North Carolina are established after 2010. We have some questions about pollution, what water samples have tested for PFOA, social determinants of health, what prevents PTSD, some general knowledge questions, what is the color of the 10-euro note, or maybe some biomedical information like find the diseases associated with upregulated genes for some study. So then zooming into one of the queries here, what do we do with it? We want to create a database query that correlates to the English language query so that once we know where to find the data, we can retrieve the data that answers the user's query. So let's talk a bit more about how we process the interpretation of a user query. We use large language models and we use some algorithmic query generation. So that means a user query enters a pipeline of different steps, and then afterwards the results are being returned back to the user. In the first step, we use a large language model to determine which of the databases are relevant. In this case, let's first assume there's only one database relevant to this. Then we use a second LLM to perform entity extraction conditioned on that particular database. So in the previous example, we talked about software vulnerabilities. So that means here the entity extraction would extract that we have a software that the user inquires about, and that is libgd. And the question is that it wants to know the versions of libdb that are free from vulnerabilities. And the LLM returns those as structured data. And then we can employ a classic algorithm that takes this information and composes a Sparkle query. We do not ask the LLM to create the resulting Sparkle query. And the advantage of this is that we can be sure that this is a valid and well-formed Sparkle query because we have full control over the composition of the query itself. Then we go to the endpoint. In this case, this is a Frink RDF store for the software vulnerabilities. We get some results back, and then we interpret those results by means of how is it presented in an appealing fashion. This is then given back to the user, but also stored internally as a new local ephemeral knowledge graph that the user can then query in further follow-up queries. In the case that a query is so complex that it needs to go to different databases, the LLM is creating a computational tree where each database lookup can be seen similar as a function call. So that means in detail, we first go to some database and retrieve some data, interpret this, then extract some data. With this, we go to another database, get some data, and do the entire process of the computational tree, and then the results are being given back. We offer a web interface where we do not only want to present the user with a static dump of the data, but offer some interactivity so that the user can actually work with this. So that means we not only have plots and graphs and maps, but we also allow for multi-turn or follow-up questions. We have some instances where the knowledge graph itself is being presented to the user in an interactive way, where a user can click on a node and then the graph expands. And so you can really see what is the underlying data composed of. And as I mentioned also before, the returned data itself is represented as a knowledge graph itself. In the follow-up questions, a user can particularly target the returned data and ask questions about that. Some of the OKN projects have their own custom websites. So in this case, our interface just redirects the user to those sites. And finally, we not only provide a website, but also an API access point. That is particularly interesting for external partners like NOAA and NASA, where Proto-OKN is just one node in their system. And this works very similar to our website that we offer. The API access point accepts a natural English query, and then the user can decide, does it want to return this raw Sparkle query, maybe to employ some query itself, or execute that Sparkle query in the same step and just have the final data being returned to it. And so with this, I'm going to present some of the examples of our website.
Secure chain and interactive elements say the user inputs the question, what are the known security issues with Qt version 6.3.2 and later? The system recognizes that this is a question that needs to be answered with data from the secure chain module and then proposes a Sparkle query to the user. The system also provides a plain English interpretation of that Sparkle. Upon the user's acceptance, the system executes the query. The results, specifically the software and version along with specific vulnerabilities, are displayed as a table. Additionally, the system recognized that a software dependency graph might be useful, hence an interactive, explorable graph is displayed as well. Each node is a software package and edge indicates a dependency. Clicking on a node explores that node's dependencies.
Pseudo-OKN and follow-up queries. The system also supports multi-turn queries. In this example, we successively build up a query by first pulling a specific state into view, North Dakota in this case, and then asking for more detailed information about this state. Here we ask a follow-up question about businesses supplying the mining industry.
SOC-KG and multiple data views. Multi-turn queries can also target retrieved values. In this example about soil organic carbon, the user asks, what is the average change in soil organic carbon stock for some plots and soil depths? This is a rather involved query, and it takes several seconds until the system generates the data from the underlying database. We see the user then request the data to be shown as a grouped bar plot. The system is aware of the retrieved data, its dimensionality, how many distinct values are in each dimension/axis, and the type of the data, such as string or integer. Based on that, the system then generates a grouped bar plot, adhering to basic design principles.
Collab next and similarities. In this example, the user provides this input. There is an environmental emergency at the Gulf of Mexico. I need to assemble a team of experts geographically close who have scientific expertise in algae so that we can provide a rapid response to an emergency. After identifying that this is a query for CollabNext, the system recognized that this involves a field algae. In CollabNext, however, concepts and topics are fixed terms, and there is no guarantee that the user-provided field exists in the underlying database. Hence, a RAG lookup first retrieves the most similar existing concept, brown algae. Then, a Sparkle query is again presented to the user, and upon acceptance executed. Finally, the latitude and longitude values provided by the user are used to rank the Sparkle output by distance. Some Theme 1 teams provide their own visualizations or advanced analysis functionalities. If our system detects that a query would best be answered by such a site, it directs the user to that site.